Okay, as promised in 8.4, we've moved on now to biological applications. We're returning now to a application that we saw briefly in chapter 6 when we talked about average value of a function. Then we talked about the velocity of blood through a blood vessel. And so as we understand, blood flows through a blood vessel, and we were talking about a finite volume of blood that passes through at any given time. So this is analogous to, for instance, the number of cars that pass through a traffic signal on a one-way street. Now, blood travels one direction through that vessel. There's no competing speeds. They all go one way, and they all go through, right? So we're going to assume that none of them gets stuck to the blood vessel walls, etc. And so we define the total volume passing through in unit, passing through a cross-section in unit time, per unit time, I should say, call it the flux. Actually, I should use a different color, huh? Because I use different colors for key terms. Okay, we're gonna use blue. So flux, really, we want to think about it is it's equivalently an amount. Okay, the total amount of blood that's coming through, and we typically write it as capital F. Oh, let me use again the original color I was using. Nope, here we go. Capital F, and it's sometimes written in this funny notation where we have an integral of the velocity or the rate through the cross-section times the infinitesimal cross-section integrated over the whole cross-section. So our cross-section in a blood vessel, we assume, is going to be a circular area, and the velocity through is always going to be perpendicular to that cross-section. Okay, there's no flow going, this way or this way. No, it's all coming out through the cross-section perpendicular to it. Okay, and V we already saw. This is the laminar flow. So we saw in chapter 6 that as a function of radius, this is going to be the pressure divided by 4 times the viscosity times the length of the blood vessel. All that fraction divided times r squared, the radius of the cross-section, minus little r squared, which is the specific ring in which which we're talking about, right? So at some given point, x, somewhere in that cross-section, it's a distance from the center, r. And so, if we wanted to find the flux, which is the total blood flow in a per unit time, right? So in a second, in an hour, in whatever unit of time we want to talk about, then we need to figure out how to integrate over the whole cross-section and what's the infinitesimal cross-section. The infinitesimal cross-section, thankfully, we can find that using related rates. So because A is pi capital R squared, or little r squared, I should say. Little r squared, because we're looking at the, as we're moving through the cross-section, right? What's the area there? Then we know that dA dt is going to be 2 pi r times dr dt. Now, if we just whoosh away all the dt part, then this suggests that the infinitesimal cross-section is going to be 2 pi r dr, which works pretty well, actually. So all that is to say that the flux here is defined and can be found by integrating with respect to r from 0 to capital R of the laminar flow times the infinitesimal cross-section, so 2 pi r dr. And I'm going to spare you all the ugly details, but in conclusion, we get something called Poiseuille's law. Poiseuille, I think that's how you pronounce it. I took French a long time ago, but I couldn't tell you. But this is a French mathematician who discovered this, and so we end up with the law that the flux, which again is the amount of blood that passes through the cross-section per unit time, is pi p capital R to the 4th power divided by 8 times the viscosity times the length of the blood vessel. Okay? What does all this mean? So if we think about how much, so here's our blood vessel, right? And here's a cross-section, okay? Think of it as, if we want to think about how quickly or how much blood is passing through at any given moment, use it. So we can figure out how much is passing through because we're integrating the speed over that cross-section, okay? So how quickly they're passing through, it's basically a higher dimensional analog of the net change theorem, which is total volume is the integral of the rate of change per time. Except this time we're not talking about time, we're talking about over that area cross-section, but per unit time, that allows us to make that conversion pretty easily. So we can multiply this by however long it takes, right? So if this is per second, then we just multiply by the number of seconds to get how much crosses through in that given amount of time. All right, so the real payoff for this is that in the next video we get to talk about cardiac output, which is really it's a consequence of applying this model, this flux model, to blood flow through the heart.